My talk is called Profunctorial Data, and initially I was going to tell a little bit about category theory, but actually I've rejected this idea. We will barely touch category theory, it only complicates things, but what we will talk about is trees. So usually trees arises when you have some expressions. You need not only to compute them, but to store those expressions somewhere in your database or send them uncomputed, or I don't know, analyze them, interpret them in any way. So you are coming with something like DSL or any other language. Or maybe you are writing your own compiler, something like that. So there you have some syntax trees that reflects your expressions, and we will actually talk about these syntax trees. Usually, to represent those syntax trees, we use data. So functional programming gives us great tool to talk about abstract syntax trees is recursive algebraic data types. So this usually looks like this. It has a lot of constructors in a real language, and you can see that it's recursive because it refers itself in its parameters. So you have a lot of trees like that. Every constructor of this AGT represents some node in your abstract syntax tree, and sometimes you actually have a lot of stages of your interpretation, compilation, untyped form, typed form, with position and for, etc., etc. And you have a lot of syntax trees that a little bit similar but not exact, that have this huge amount of constructors, and then you come to this problem when you need to write a lot of lookalike functions to manage those different but very similar data, and you naturally come to the problem, to the thing that's called expression problem, the problem when you want to some modularity built into your language definition. Some people even think a language as a natural tool for modularity, an expression problem, its solutions as a natural solution for their modularity. So even if you have some business application and you have a lot of models that are correlated somehow, that calls each other, you can sometimes reflect it as a language problem when you have different small sublanguages. When you compile those sublanguages into larger languages and translate them to a more and more specific and low level. So one great tool to talk about data is equivalence. Two data types are called equivalent or isomorphic. If we had a couple of functions, one transform this way, another transform it back, and we have some equations, like if you transform this way then back, or transform back then this way, you will have the identity transformation. What does this mean? This means that none of these transformations does not lose information. So both of these types that are equivalent or isomorphic, they actually have the same level of information hidden in them. So they are just the same thing, but from different angles. So we know equivalence, for example, as equivalence of sequence type. Each sequence type is equivalent to each other, and those transformations are usually trivial. Product types can be seen equivalent to function types. For example, pair can be seen as equivalent to function from Boolean. So the first component will represent a then value, and second component will represent the else value. And we can easily construct a function that translate them from another. And another interesting form of equivalence is equivalence of strict value to some thunk that eventually will compute this value. So you can capture any value in the thunk, and you can compute thunk, give the strict value back. So we can actually construct a little bit interesting type that is the same, actually the same thing that as a thumb. So it's a lazy form of type A that expects some function that that wants A as a domain, and it's happy to provide this A value it has or going to compute to just give back the result of this function. So this lazy form is equivalent to the original strict value of A. And we can actually show this providing two functions and easily prove that they're composed nicely into an equivalence. So to construct a lazy, we just provide our value to any function that it. To compute from lazy, we just recover our value providing the identity function from A to A. So this really interesting trait, and we will use it several times during our presentation. So remember how it looks. So the key component is parameter here, the type parameter here. So this universality gives us this whole equivalence. So let's talk about representation. One thing where we can use those equivalents is abstraction of representable functor. Representable functor is a functor that is equivalent to some function functor. So that means we have some domain type and the whole functor f equivalent to functions from this domain. And we have these two functions representing the equivalence, transformations to function type and from function type. This is usually how this representable functor is defined. So an example of representable functor is of course a function, and its domain will be its representation. Another form of representable functor is, as we said, is a pair. So we represent a function from a functor that consists of a couple of values A as a function from Boolean. So this couple is a representable functor. And actually, if we need, we can construct representable. We can actually construct the representable functor by its domain. So let's think of this data type, and I'm user, and let's construct this trait that actually mirrors the structure of our NO. So every constructor transformed to a method, every constructor parameter transformed just moved here as a parameter of the method, and we have this all reflection, and functor argument is here represented as a result type of every method. So we can actually prove that this is a correct form, a representable functor. So the user is indeed a representation of our functor from users. So as you can see, method definitions correspond to pattern matches, and method calls correspond to a construction. So this is usual correspondence between data and code data. So Let's recall our lazy type, since it's really helpful. Let's think of this as a representation of some functor. So we have some functor representable that is equivalent to function from A. What does this mean? That means that we can actually replace this function down here and gain an equivalent type to our lazy representations of A, but it's determined in terms of our functor. So we don't need our original type. So actually, representation of F, this wrapper trait, is equivalent to our original domain that we desire from our functor. So that means that we can actually really simplify our representable functors, replacing the abstract type member with a pretty much concrete type. And we can actually exile this method index from the type class because it's trivially implemented in terms of wrapper. So this representable functor can be actually be defined in terms of a single abstract method using this wrapper trait. So this actually means that yes, wrapper from user is equivalent to the original enum user type. But what if we have some parametric type that is non-functor and is not representable? What if we have some reference to this R type here in the parameters section? What do we have? Is it corresponds to some type? How do you think? Actually, yes, we can construct some algebraic data type that is also equivalent to representation of this non-functor trait. And as we can see, these enumerations became recursive. So the appearance of this type parameter means recursion in our type definition. That's interesting. We can actually prove that. We can use a full construct. As usually, we replace every method definition corresponds to some pattern matching, and every constructions corresponds to some method call. That's how its equivalence is defined. So have we achieved something? Have we invented something new? Actually not. Actually, this was known for, I don't know, decades. It was known for as a charge encoding of algebraic data types, or Bernoulli encoding, or tagless final style of data representations. And yes, it's a general form of representing of recursive type without recursive typeability in your language. So you can represent Boolean with this from bool trait, or natural number that is already recursive as this from net trait. You can see this usual two parameters in your charge encoding, or these two parameters, function parameters in your charge encoding from list if you have charge encoded list. So this is really, really old and well known. And of course, we know that we can take any algebraic data type and represent it in a charge encoding. So what we have new in our shiny Scala that can add some new aromas to this old, I don't know, almost century-old charge encoding thing. So actually, Scala has subtyping and variance. So if we only take our representation trait and add their minus, we actually tell that instead of F, we can actually widen this representation, meaning that instead of this base representation trait, we can have this trait mixed in the in the intersection with bunch of other traits. So we can actually make this representation extendable. What does it mean? For example, if we have church-encoded representation of two single case classes, we can find that church-encoded representation of the intersection is actually a union of those case classes. So this is generally true that for non-recursive traits, non-recursive types, our representation is equivalent. Representation of intersection is actually equivalent to union of representation. You can use it in Scala 2 when you do not have union as a primitive type, but in Scala 3 we have. So we actually don't need this much in Scala 3, right? Or do we? So imagine you have a lot of languages. Each language is a church-encoded form of some. So you have this trait for church-encoding of this Boole's language. You have numbers trait that can use it for church-encoding some numbers language that consists of some basic operation numbers, and you have some basic language of comparison, and you can have church-encoding version of that. So actually, if you compose all those traits using intersection, you can have a trait for church-encoding a new form of recursive language, when actually some condition like and could refer to some expression in some expression from other sublanguages. So this is, we cannot do using just union. This is not a union of recursive type, because if you take union of two recursive types, each of its nodes can have as a subnodes only corresponding sublanguage. But here we just really combine several languages in a single language. So we really have extensibility. Extensibility means that if we construct using our wrapper thing some expression, it's actually reflects something like an extensible markup language, right? When you have a different kind of nodes, you can actually mention those nodes somewhere in the header. And here you can mention all of node sets, all of your three combiners in the type of your expression. So your type of your expression actually mentions all of sublanguages you are using. And if you need to abstract, if you need to widen it, if you need expressions of a wider languages that can consist of more sublanguages, you can use this expression straight away. So church-encoded thing, church-encoding have actually a nicely works with constructions. You can easily define some constructors in an easy form, just a constructor of these representations that will call the appropriate functions from your arguments. But what about pattern matching? So what if you don't need to fold the whole tree at once? What if you need to go just one level down? So for example, you have some natural number, church encoded, and you just need to compute this function that is, you can call it pref or pred as a predecessor of soft minus, which means that if we have 0, its predecessor is always zero as well. And if we have some non-zero number, its predecessor is number -1. So can we compute this simple function that should be computed as a simple pattern matching of this nature? That actually it turns out that we need to rebuild our subtree from bottom up, and this is really frustrating. This is one of the simplest church-encoded types, and this expression is already really complex, and it will become even more complex for other types. So what tools we have to overcome this? So natural thing to work with this generalized recursion is what is called recursion schemes, which works with fixed point, with functor fixed point. So functor fixed point of some functor is some type that is equivalent to functor applied to this type. So fix of f equivalent to f applied to fix of f. And this opens a huge amount of things that calls morphisms. This usually called catamorphisms. This is called anamorphism. There are histomorphism, futuremorphism, prepomorphisms, and those are usually some kinds of folds, unfolds, or refolds that combine unfolding with folding. And actually, all this gives access to traversing your tree very nicely, to give all the information from your tree or to constructor free, even using an effects on the way. And usually, this means that you need at least traverse instance for your base functor that you're fixed pointing now. So it's really handy, and this is widely used, but not as normal programming, used usually for some compiler buildings, or for some heavy DSL writers, or some, I don't know, data schemes, something like that. And we can actually very easily make this form extensible. Again, in Scala 3, we can just define this functor as this functor parameter is as a covariant and require a covariance from this functor. Since it's always a functor, it will be always covariant, so you don't need to worry about this plus. But this plus gives us a real extensibility. You can have all the folding and folding tools of your favorite zygomorphisms, but also you have some extensibility. So if you have some languages, usually they are defined like this. So we took recursive types, define sublanguages, and rip them only one level. So right now this algebraic data type is parameterized, and each of these languages represent just a single node of some language. And recursive references replaced with this reference to the type parameter. We can just push each of these languages inside fix, and we will just, as a result, it will give us a language of bools, of numbers, all of comparison. Or we can actually use a unions. We can use union types from Scala 3 and build a fixed point of this combined recursive types. So here we build an expression that consists of numbers and comparisons, and if we need it as an expression of a wider language, we can naturally transform it using just application, because it's really a subtype. So this is all good. But we have some problems. For example, it's not obvious how to compose these traverse instances for union types. Also, if we talk about the real effects, about an effect handling, what is effect handling? Usually that means that you define in some complex language and you can translate some parts of language into something else. So, for example, this is a simple example of handling. We have this sub-expression, and we know this sub-expression can throw some errors. So that means that there are some expressions that throw errors. So we can we can take these expressions and actually handle it, and we can actually cut them from the resulting language, and we will know that resulting expression does not have this arithmetic exception effect. Generally, this means that we can have languages that consist of two sublanguages, and we can provide a handler for one of those sublanguages, translating him into the pure other. And as a result, we can have language that consists only of one sublanguage. So we just cut half part of the language using handling. This partial handling is super handy, but it's not trivial to implement actually. For example, we can implement it for our fixed point forms using pattern matching, right? We can just go through every node, pattern match every functor that we use, and if we meet our desired functor that we handle right now, we just call the handler. If we found something else that we go down, recursively call handler for the sub-expression. So this actually works, but it's super ineffective, meaning every handle needs to traverse the whole tree. And actually, it's not that useful in this form. Therefore, we need some other form. So now we came to the actual star of this talk, our Profunctorial encoding that I've used in different forms several times. It actually worked. It actually working, but today's talk about a little bit about extension even of this format. I'm currently trying to write a library for it, but it's not there yet. So if you are interested, contact me later. So let's start from our trait for church encoding. We have this trait, we have this R in our parameters, meaning that there will be a recursive reference to the thing, and we have this invariant type. So it's not covariant, it's not contravariant. And we make it automatically devariant, making we transform each of reference inside the parameters to the one type parameter, and each of the reference in the result to the other type parameter. So resultant trait will be actually contravariant on one parameter and covariant on other parameter. So this is actually looks like something if you know something about profunctors, but we will not mention them heavily today. So we get this, and how can it help us? So actually, if we have this base functor, for example, for our fixed points, for our recursion schemes, we can tell this trait is actually equivalent for a function type from this interesting function type, where it has its base functor on the domain and its other parameter as a result. So it's one of two fundamental profunctors that we can construct for our base functor. That is a very fundamental relation between this profunctor and this functor. So what it gives us? What value can we have here? So we can construct this thing that actually should remind you of something like representation. But representation, unlike repr, it is actually a little bit recursive in its definition. It mentions itself inside itself. So how can we translate it? So actually, we can take some concrete functor. We remember that this profunctor is equivalent to a function from some base to some result, and we can actually say that this trait is equivalent to some of this trait, right? When we have this function and the actual argument, and this trait should remind me of something, because it's really our lazy form of this f of wrapped f. So that means that wrapped of f is equivalent of f of wrapped of f. What does this mean? That means that wrapped is really a fixed point of our base function. So really, if p some profunctor for some base functor, that layer represents actually its fixed point. So actually, what we just did there, we just constructed a church encoded fixed point for the base functor using its profunctor representation. That's what we're doing here. So let's take some concrete example. We have our recursive data type, we have our profunctor, and we have our layer type from user. It's actually equals to, as we know, this trait when we have this profunctor already through the equivalence transformed to these functions, and this actually equivalent to the user f applied to wrapped user. So we can actually use this correspondent a lot of times. So we can actually say that is user f of user weights, and definitely many times. So this actually things is equivalent to a tree constructed from nodes like this. So we actually just represented a language consisted of these nodes. So to work with fixed points like this, we need some type classes, right? So for example, we need to prove that our profunctor is really a profunctor for some base functor, and we need to prove that f is functor and f is traversable. So this call we can actually saw is something like co-representability of profunctor. So we can draw it as a type class like this. It actually looks just like the representable functor, but our base thing is just a functor instead of concrete value. And actually, we can replace it, as we done before, with some wrap type and reduce it to a single abstract method type class. So this is the first type class we would need. Second type class tells us that f is a functor. So this would mean that our thing is a profunctor. It has right map, right? So now we need a left contravariant map. We need to prove that f is a functor, and this is just really straightforward. We just take a function, take a profunctor, and if we can apply this function inside the left side, given this L as a result, so we can actually say that yes, base functor is definitely base is a function, and we can have this. I suppose it's very beautiful. One of the most beautiful things about this thing, how we can show that base functor is traversable. So we can just P of A and B, we get some applicative functor, and we just can, if we can apply F to both sides, that's actually equivalent to a traversable instance of F, if we already know that f is a functor. So actually, if you really replace p with this function here, you can have something that really looks like a sequence method of the traversable type class. So actually, a not very important thing that we can combine all these three type classes into a type class with a single abstract method, and we can implement all of these three methods using this single abstract method. That's not the point. The point is that it's really a representation of a fixed point. So we can do all of our favorite prepomorphisms, all we so like, and actually we can do this using these representations. We need a lot of additional special maps, and we use this pro-traverse every time when we need traversable instance for the base fountain. So this is really helpful. And if you seen, we defined it with minus here straight away. So that means that our layer type, our fixed point, is extensible automatically. So that's, for example, how we can define small languages, small model-like languages for our representations. If of those is a profunctor, each method that recursively references some subtree uses this first parameter. Each of the method returned this second parameter. For each of these traits, we automatically can derive this traverse instance. And we can say this is extensible. So we can define some expression. It's no hard to make a specific functions, but we actually don't really in hard need of them. We can just use this layer things for defining our expressions. And if we have a wider language, we have automatic widening. We have automatically inclusion of any sublanguage into a wider language, and this is really helpful. So we still don't know how to combine traverses. We still need to how partially handle effects, we talked later, and we actually maybe need to do something with index types. We might like our languages typed, but that would be in the very end. So let's talk about effects. One super cool thing that Scala 3 added is called a selectable trait. So Scala 2 already have a dynamic type, which actually can simulate dynamically type structures when you can use some maps as they have actual values, and have structural types. So structural types are super cool, but they could only use reflection in Scala 2. They can only call these methods using reflection, but in Scala 3 it actually combines those things. You can have structural typing for dynamic structure. That means you can have some map of any values. If you at some point ensure yourself that this map have the structural types, you can use it safely. You can use this age, which lies in some map, just a field, just a value. You can use name, just a value, and you already remember types for each of your values. So this actually gives us TypeScript-like abilities. Why is it cool? It is cool because we can have merged some dictionaries. We can have two dictionaries, each of have has its own set of vowels, and we can actually merge them into a wider dictionary that has all the names, all the values. So, for example, if we have two structural types, we can actually merge these dynamically structured, dynamically typed structural types into a single large type which type will be as an intersection of these structural types, so that it will have every value that consisted here. What does it mean? We can use it for our Profunctorial encoding. So we can use some special dictionary to contain our Profunctorial instances with the Profunctorial objects with the protraverse instances. So we can build a large map. So all the code that we'll go later is a little bit simplified version of the real code, because real code is now work in progress. But you can actually have an idea of what is going here. So you can have each of these languages, but the real types which you would use in your typing would be not these traits, but this single valued structural type. So it should remind me of something like cake pattern, or maybe of Zio model pattern version 1. Actually, it looks like Zio version 2 and 3. It doesn't matter, because it uses the same trick. We are typing dynamic heterogeneous maps. And we will use this heterogeneous map, this structural typing for the heterogeneous maps as our base for typing of our Profunctorial things, Profunctorial functions. So starting from this dictionary, we can redefine our layer to unwrap a single layer from a little bit complex type, which we call as pro data. And we can define a new type handler that translates some language or some set of languages to some different set of languages, maybe even intersecting with the original. And our actual pro data will have two types of constructors, just like, for example, a free monad. It can construct a single layer, so it could introduce a node of your abstract syntax tree, or it could eliminate some sublanguage using a language. So if you have some expression, some term that uses a couple of sublanguages, you can just take one of the sublanguages and retranslate it to the other, cutting this sublanguage entirely, because in the result you have profound data that consists only of this language. So
hello, Oleg. I'm afraid we're running out of time.
So how much do you have? 5 minutes?
You've gone 5 minutes over into your question time. So it's possible to do a quick wrap up?
Yes.
Because we have got some people waiting for lunch.
We have this handler thing that allows us full elimination in our modularity. So we can have a very complex relation of models, and we can just cut. And we can have some higher kind that actually represented the types with a lot of holes, but actually it's all a technicality. You just replace all normal functions with the polymorphic functions. It's not that interesting. And thank you.
That was fantastic. Thank you very much.